Hello, everyone. Today we are going to talk about section 2.3. This is modeling with linear functions. The first order of business basically is to discuss a problem solving strategy or the problem solving strategy. So, what I have in front of us is a kind of broad problem solving strategy. There's maybe a bit more detail in the textbook. I kind of tried to paraphrase what they had, and here, let me make sure these look indented. I kind of tried to paraphrase and maybe make it a bit shorter, or word it into ways that I thought were better or clear. So the problem solving strategy here is, first of all, the 0th step. Before anything else, we have to read the problem. This seems obvious, but there are many questions that can be resolved simply by fully reading the problem. A lot of the time we don't read the problem. We look at the problem for numbers and we start to immediately try to do math. We need to actually fully read the problem so that we can understand what's being asked of us and what those numbers mean in context. So after that, step 1 here, I have read the problem as a 0th step. It's the most important. It comes before everything. Step number 1 after that is identify changing quantities and clearly define any descriptive variables that represent, or rather, to represent these changing quantities. At this point, you might draw a picture, you might define a coordinate system. So you might draw a picture or create some axes is what we mean, like this, so that you can graph something. Whatever this graph may look like. It may look like a straight line, right? Or it may look like whatever. It could be a parabola, but step 2 is to reread the problem. At this point, we want to identify important information, such as any values for my variables or values for parts of our functional model, such as slope and initial value. So if we see anything that could be a rate of change, that's going to be a slope. If we see anything that could be like some starting value or initial value, we want to make note of that as well. Then identify a solution pathway. How can I use the information that I've been given and the things that I know in order to find what the problem is asking for? At this step, we might build a table or find a formula. Step 4 is to solve or evaluate using a table or the formula that we've created. Step 5 is to reflect on our answer. Is the answer that we obtained reasonable? Are we answering the question that is being asked, right? For instance, if you're trying to calculate the height of something and you get a negative number, then that's not reasonable, right? Something cannot be negative 5 feet tall, right? Similarly, if, say, the question is asking what year something will happen in, right? And you get the number 23, but this 23 stands for, say, 23 years after 2004. Then this is not your answer. This 23 is not your answer. In that case, 2027 would be your answer, right? So we have to make sure that the number that we're providing is actually answering the question that's being asked. And also, step 6 is to clearly convey your answer. Make sure that you're using appropriate units. Provide your answers in full sentences whenever you can or whenever it's applicable. I also wrote out a shorter version of this. This can be reduced to a few shorter sentences that are less in depth. Again, once the first thing that we have to do before anything else is read the problem. Then we have to understand the problem. Understanding often involves rereading, right? Then we create a plan, and then carry out the plan, and then we reflect on our answer. This is the same idea, just shorter. So let's look at an example of a problem. And let's apply our problem-solving strategy. Let me increase the font size here. There we go. Emily saved up $3,500 for her summer visit to Seattle. She anticipates spending $400 each week on rent, food, and fun. Find and interpret the horizontal intercept and determine a reasonable domain and range for this function. Okay, so I've read the problem. This is good. I need to identify any changing quantities. So it looks like number of weeks could be a changing quantity, right? So let's see. Things that are changing. This would be number of weeks. So I can define a function. Let's create some variables here, right? Let's say that our output here is M, capital M, for money. Here, let me say this is our output. Capital M for money remaining in dollars. Our input will be T, which will be time in weeks. Okay, and now let's see, we have some numbers in this problem as well, right? Emily saved up $3,500 for her summer visit to Seattle. She anticipates spending $400 each week. So we have some initial value here, right? Emily saved up $3,500. So $3,500 is the initial value for M. And she anticipates spending $400 each week, right? So the amount of money is decreasing by $400 each week. Right? Here, let me use the dollar sign here. So I believe that this allows us to set up an equation or formula. M of t is equal to 3,500, which is our initial value, minus 400 times t. Because 400 is my rate of change. Really, it's negative 400 is my rate of change because the amount of money in Emily's bank account is decreasing by $400 a week. Now, I have a formula. Let's look at the problem again to make sure that we're trying to find what's being asked for. We'll want to find and interpret the horizontal intercept and determine a reasonable domain and range for this function. Okay, let's find and interpret the horizontal intercept first. So the horizontal intercept is going to occur where my output is equal to 0. We're going to cross the horizontal axis where the output is equal to 0. So I'm going to set my output equal to 0, and I'm going to solve for t. see, if I add 400t to both sides, I get 400t equals 3,500. Then whenever I divide both sides by 400, I get t equals 8.75 weeks, because time is in weeks here, right? So this is my this is the t value of my horizontal intercept. Of course, the m value here would be 0, right? So because my horizontal intercept is where my output value is equal to 0, this horizontal intercept is where the amount of money that Emily has is equal to 0. So this means that so the interpretation of the horizontal intercept, let me write this. This means that after 8.75 weeks, Emily will run out of money. Oh. Let me erase that. There we go. After 8.75 weeks, Emily will run out of money. Let's see. We also wanted to find a reasonable domain and range for this function. Maybe I should write of a little lower so we can see this is clearly on a second line. There we go. So a reasonable domain well, we said that Emily will run out of money after 8.75 weeks. My domain is my set of inputs, so I'm looking at the number of weeks that Emily can spend in Seattle here. The minimum number is 0 weeks, right? Technically, you don't have to go to Seattle at all. And then the maximum number of weeks would be 8.75. And I would include both of these because these are both potential options here, right? And of course, I'm assuming that Emily purchased a round trip ticket. So, you know, there are no additional like travel costs. For a reasonable range, we said that, so since our range is a set of all outputs, the minimum amount of money that Emily goes home with is $0. That's if she spends all 8.75 weeks in Seattle. The maximum amount of money that she keeps is all $3,500 if she doesn't go to Seattle at all. Therefore, the range here would be 0 to $3,500. And this is precluding the possibility of going into debt to stay here longer, for instance, right? I mean, if you save up $3,500 to go on vacation, you probably shouldn't go into debt to stay on vacation longer. I mean, that's a lot of money, right? Okay, let's look at another one. Let's look how to solve some of these other ones. Jamal is choosing between two moving companies. The first, U-Haul, charges an upfront fee of $20, then 59 cents a mile. The second, Budget, charges an upfront fee of $16 and then 63 cents a mile. When will U-Haul be the better choice for Jamal? Okay, so let's see. I think I can define two functions here. I think that the input for both of them is going to be M, which is miles driven. And I'm going to have a couple of separate outputs here. I'm going to have, I'll call it U of M. This is the cost in dollars for renting from U-Haul. And B of M. This is the cost in dollars for renting from Budget. Now, if I read this again, U-Haul charges an upfront fee of $20, then 59 cents per mile. Budget charges an upfront fee of $16, then 63 cents per mile. So it looks like for each of these, I have an initial value and I have a rate of change. Okay. Now, of course, we're given the upfront cost in dollars and the rate of change in cents, but converting from cents to dollars is very simple, of course, right? So U of M, I can say that this is, so the upfront fee is $20 plus 59 cents in dollars is 0.59. This is times M. B of M is, let's see, the upfront cost for Budget is $16. And the rate of change was 63 cents, which in dollars is $0.63. And I multiply that times M. So after some amount of miles, because U-Haul has a smaller rate of change, U-Haul will be cheaper after we reach a certain number of miles. So what we have to do is find how many miles that is, and after that point, U-Haul will be the cheaper choice. We have to find where these two are equal to each other then. We have to find where their cost is equal to each other. Because after that, again, U-Haul will be cheaper. There are a couple ways of doing this. We could graph this and find the point of intersection. I'll show us that in a second. The way I'm going to do it first is I'm going to just set these two equations equal to each other. So I'm setting U of M, which is 20 plus 0.59M, equal to 16 plus 0.63M, so equal to B of M. And let's solve. Let's see. I can subtract 16 from both sides to get 4 plus 0.59M equals 0.63M. I subtract 0.59M from both sides. And I get 4 equals 0.04M. To solve for M here, I have to divide both sides by 0.04. And I get that M equals 100 miles. This means that after 100 miles, U-Haul is cheaper. Now I can, of course, go to Desmos.com and graph both of these. So whenever I graph both of them, notice at first that I don't see anything on this graph. I don't see anything on this graph at first. This is because my window is not, these are outside of the scope of this window, right? Notice that the highest that this goes currently is 7. So I'm going to zoom out and I'm going to scroll up a little bit because I know that my initial values were 16 and 20. Okay, so I see the lines now. You can see that I typed the equations in here. I simply used x's instead of m's. And I'm going to scroll so I can zoom out. And you see the red line goes from being above the blue line to being underneath it at some point here. So in Desmos, if we want to find this point of intersection, we can actually just click somewhere near where we think it is, and it gives us this dot here. And it just tells us what the point of intersection here is. So this input value is 100. So after 100 miles, the costs of U-Haul and budget will be equivalent, and that cost will be $79. So the price point that they are both equal to at 100 miles is $79. Let's keep going with a few more examples here. Just increase that a little bit more. There we go. A town's population has been growing linearly. In 2004, the population was 6,200. By 2009, the population had grown to 8,100. If this trend continues, predict the population in 2013 and find when the population will reach 15,000, or when will the population reach 15,000. Let me separate this on it. Oh, sorry. Let me separate this on a different line here. So let's see. Notice that I have 2 inputs and 2 outputs, right? I have 2 years and I have 2 population numbers. So let's define our input to be t, and let's say this is years after 2004. Because this way our numbers will be smaller and easier to work with. And also if we were to graph this, the graph would be easier to find. And our output will be P of t, the town's population. So, if t is the number of years after 2004, this means that 2004 itself is 0, right? T would be equal to 0, because 2004 is 0 years after 2004. So the population in 2004 is 6,200. So P of 0 is 6,200. Then the year 2009 is 5 years after 2004. So we'd be looking at P of 5. And the population 5 years after 2004 is 8,100. So now we need to set up, to set up an equation, we have to find the slope of this linear model. M here is equal to P of 5 minus P of 0 over 5 minus 0. P of 5 is 8,100 minus P of 0 is 6,200 over 5 minus 0 is 5. This is 1,900 over 5. So M is 380. And I have that P of 0 is 6,200. So my initial value here is 6,200. This means that my equation that represents the linear model of the population of this town is P of t equals 6,200 plus 380t. So now that I have a formula, let's see, I want to predict the population in 2013. In 2013 is 9 years after 2004, so I'm looking for P of 9. This is 6,200 plus 380 times 9. This is 6,200 plus, let's see, 2,700, let's see, what is this? 3420. And this is 9,620. So the population in 2013 is 9,000, or let's say will be maybe I should write this better. Our model predicts that the population, let's see, okay, our model predicts that the population in 2013 of this town will be 9,620. That could probably be worded better, but I just wanted to clarify. Of course, like realistically, the town's population could stray from this model, right? But this is what our model predicts. And we want to find when the population will reach 15,000. When will the population reach 15,000? So I want my population, or my output, to be 15,000. And I want to set this equal to 6,200 plus 380t. And here I'm trying to solve for t. I'm solving for time. So I subtract 6,200 from both sides. And I get, let's see, 8,800 equals 380t. I divide both sides by 380. And here I'm going to get t is about 23. It's going to be 23.158. So our model predicts that the population will reach 15,000 in 23 years, or in the year 2027, because 2027 is 23 years after 2004. We have a few more examples to go through. Anna and Emmanuel start at the same intersection. Anna walks east at 4 miles an hour, while Emmanuel walks south at 3 miles per hour. They're communicating with a two-way radio with a range of 2 miles. How long after they start walking will they fall out of radio contact? Okay, so they start at the same point. Then Anna walks east. And Emmanuel walks south. So here we have Anna walking east. At 4 miles per hour. Down here we have Emmanuel walking south. At 3 miles per hour. And we have, there's no dotted line tool. I'll make a purple line though. We have a distance between them, represented by this purple line. So we want to find when the distance between them will be equal to 2 miles, because that's when because after that point they're going to fall out of radio contact. So let's see, we need to use our information so that we can do something with this triangle that we've drawn. We said that Anna is walking at 4 miles per hour and Emmanuel is walking at 3 miles per hour. These are both rates of change. So this means that I can write formulas for the distance that each person has walked. I can say, for instance, A of t is equal to 4 times t, and E of t equals 3 times t. Now I can label the sides of this triangle. And let me swap colors here. I can label the sides of this triangle 4t and 3t. And because this is a right angle, because Anna is walking east and Emmanuel is walking south, the angle between them is a right angle, right? That's how a compass works. That means that this long side, this purple distance, is the hypotenuse of this triangle, which I can use the Pythagorean theorem to find a formula for. So let's call that long side of the triangle d of t, the distance between them. This is equal to a of t squared plus e of t squared. Oh, d of t squared rather is equal to this, right? So d of t squared is equal to 4t squared plus 3t squared. Whenever I take the square root of both sides here, I get that d of t is equal to the square root of 16t squared plus 9t squared, which is the square root of 25t squared, which is 5t. D of t is 5t. Now we could say plus or minus 5 t. But distance has to be positive. So we can just take plus. We can say that this is 5t. So I want to know when this distance is equal to 2 miles, because after that they're going to fall out of radio contact. So I simply take 5t and set this equal to 2, and I solve for t. That's how long this will take. T is equal to 2/5, or 0.4. So they will fall out of contact. In 0.4 hours. Or if we wanted to say this in minutes, this would be 24 minutes. And one more. This one looks longer, but it's not bad. There's currently a straight road leading from the town of Westboro to a second town 30 miles east and 10 miles north. Let's see. In fact, let's go ahead and start. Let's start a drawing. Or maybe we should read all the way through first. Partway down this road, it junctions with a second road, perpendicular to the first, leading to the town of Eastboro. If the town of Eastboro is located 20 miles directly east of the town of Westboro, how far is the road junction from Westboro? So let's read through this again and draw a picture as we go. There's a straight road leading from the town of Westboro to a town 30 miles east and 10 miles north. So let's make a coordinate system here. I'm just going to define Westboro as being right here. I'm going to call it W, so I don't have to write all out Westboro. And we're saying that 30 miles east and 10 miles north. Oh, let me erase that. Sorry. 30 miles east and 10 miles north, there's another town. Let's see. Let's say the other town is over here. This is other town. I'm going to call this O, or here, I'll say other town. This is at the point 30, 10. Eastboro is 20 miles directly east of Westboro. Let's see. Partway down this road, partway down the road, it junctions to a second road perpendicular to the first, okay, leading to the town of Eastboro. So maybe about right here. And because this road is perpendicular to the first road, that means that there's a 90-degree angle here. And we said that Eastboro is located 20 miles directly east of the town of Westboro. So Eastboro is at the point 20, 0. So I want to find the distance that this junction is from W. Okay, so we have a few things that we have to do in order to do this, but it's not too bad. Let's see. The first thing that we should do is we should find the equation of the line going from Westboro to this other town. Also, Westboro is the point 0, 0 here in my coordinate system. Well, let's see. The slope for the line from Westboro to the other town is going to be m equals 10 minus 0 over 30 minus 0, which is 10 over 30, which is the same thing as 1/3. The initial value here is 0. Not my horizontal intercept, but my vertical intercept here is 0. So the equation of the line going from Westboro to other town here will just be, we'll call it w of x equals 1/3 x. Now, we have to find the slope of this other line, and we have to find the equation of this other line. And we have to find where this other line and this first line intersect, and then find the distance from Westboro to that point. So let's see. I guess we have to know how to find the equation of a perpendicular line, right? I don't think that we've discussed this, but parallel lines have the same slope. Perpendicular lines, that means lines that meet at a right angle, have opposite reciprocal slope. And what we mean by this is if I have two slopes, m1 and m2, then m2 is equal to negative 1 divided by m1. So I said that this line is perpendicular to w of x, which was 1/3 x. So my m2 here is going to be negative 1 divided by 1/3, which is going to equal negative 3. So I need a line that has a slope of negative 3, and it passes through the point, it passes through Eastboro, so it passes through the point 20, 0. So I need to keep this point 20, 0 in mind whenever I'm doing this. So I'm going to say, I'm going to call this line e of x. This is negative 3x plus b. So we're going to find e of 20. This is negative 3 times 20 plus b. Well, e of 20 is 0. So this is negative 3 times 20 is negative 60 plus b. I add 60 to both sides, and I get that b is equal to 60. This means that e of x is negative 3x plus 60. I said w of x is 1/3 x. I can find where these two things intersect by setting them equal to each other. Negative 3x plus 60 equals 1/3 x. Let's see. I can add 3x to both sides. 3x is the same thing as 9/3 x. So on the right hand side here, I'm going to have 10/3 x. Then I multiply both sides by 3/10, which is the reciprocal of 10/3, so that I can cancel the 10/3. 60 divided by 10 is 6. 6 times 3 is 18. 18 is equal to x. If 18 is x, y is just w of 18, which is 1/3 times 18. And this is 6. So the point 18, 6 is where these roads intersect. It's where that junction is. Now I want to find the distance from Westboro to this junction. So I want to find the distance from 0, 0 to 18, 6. So my distance formula here, let's see, square root of 18 minus 0 squared plus 6 minus 0 squared. This is the square root of, let's see, 324 plus 36. This is the square root of 360. And if we type that into a calculator, we get about 18.934 miles is the distance from Westboro to this junction. And that's section 2.3. It's just about taking the stuff that we already know how to do and applying it to solve problems. Really, the only new thing we covered is this idea of parallel and perpendicular lines and this idea of problem-solving strategy. I hope that y'all have a great rest of your day. And I'll upload a review video for test 1 shortly.